Hello, my name is Aryan Tashkori, and today I'm here to present to you the Raytheon drone competition from the Mechanical Engineering Senior Design Team. The Raytheon Full Send competition is hosted yearly. This year, we had to design and build a pair of vehicles, one unmanned aerial vehicle and one unmanned ground vehicle. The unmanned aerial vehicle will go around the entire field to locate an Aruco marker. Once it finds the Aruco marker, it'll send a signal on its location to the ground vehicle. The ground vehicle will then move to that location, carrying an 8-pound payload, and deposit it at that location. Points are awarded based on completing the challenges and several qualification or quality tests done before the competition began. To do this, we partnered with an electrical engineering and a computer science engineering senior design team. In the video that you see, we are using a drone that will be used during competition. In the video, you can see that on the bottom left-hand side, we'd plotted 6 points, and that the drone is autonomously flying to those 6 points. The difference between this and the competition is that during competition, we will not be manually plotting those points. Instead, the drone will automatically scout a path using the border that you can also see on the bottom left-hand side, using the blue markers. Now, for the design of the drone itself, we looked at 2 key features that were needed. The first being a flight time of 10 minutes. The entire competition has a duration of 10 minutes. We want to make sure the drone can stay aflight the entire 10-minute time. The second being the thrust to weight ratio. As winds are unpredictable during competition day, we need to make sure we design the drone in order to be able to modulate enough in the wind to stabilize. For this, we looked at 3 components. The first being the carbon plate that houses the electronics safely. The second being the propeller guard that not only protects the drone but is a safety requirement by Raytheon. And the third being a motor propeller combo that gives us enough thrust for our purposes. The first component is a carbon plate. We use SolidWorks and topology optimization to inspire our choice for a lightweight yet stiff design. The material that was used was a 1 1/8 inch quasi-isentropic carbon fiber by Hillside Composite. They also were able to manufacture this plate for us after ordering using their water jet cutting system. We used FEA, specifically finite element analysis in ANSYS, in order to find the stresses at certain locations, influencing our design from what you see from Figure 5 to what we now have in Figure 6, using a 20-foot free fall. The second component is the propeller guards. Originally, we had a design as such in Figure 7, however, as seen in Figure 8, it fractured too easily at this end. And so to fix this, we added stiffeners at the bottom of the prop guard, resulting in the design that you can see in Figure 9. Lastly, we look at the propeller and motor. We use thrust testing using a thrust stand in-house, and based on this, we looked at the batteries. Using the 3S system, we were able to fly for 14 minutes. However, comparing the 45% throttles to the 4S system, we would not generate enough thrust in order to modulate in the wind to stabilize. So the 4S system was used, which ended up having a 10-minute flight time and enough thrust to modulate in the wind to stabilize. The UGV was also created by the mechanical engineering team. In the video, you can see it moving towards the payload location, and the payload that's on top of it, which is the medkit, which is 8 pounds. The UGV was designed with 2 things in mind. First being the housing of the electronics using the plate, and the second being the actual payload delivery system. The payload delivery system uses a servo gate, which when closed has gravity and the rollers roll down the payload onto the Aruco marker. Based on some testing, we also had some issues with grass getting into the UGV itself, and to make sure that it's safe from environmental components, we also designed an electronic cover for the actual UGV. The payload on the left-hand side is seen on top, and the entire completed component on Figure 14 is the completed UGV. The following individuals are specially recognized for their assistance during the competition, as they helped us either manufacture or advise us through the creation of the drone and the UGV, as well as the programming that is involved behind them. Thank you to these individuals, and thank you for watching our presentation today.